Hey guys, this is David. In the previous lectures, we have only talked about how to analyze the kinematics of a linkage system. This video will be our first step to dynamic analysis. Okay, first of all, what's dynamics? Dynamics is a study of both kinematics and kinetics of a system. I guess the word kinematics shouldn't sound like something new to you by now, because that's what we have been learning so far. As for kinetics, let me read the definition out for you. Kinetics is the study of motion and its relationship with the forces that produce that motion. So basically, both kinematics and kinetics care about the motion of a system. The only difference between them is just that when it comes to kinetic or dynamic analysis, we also care about the forces that produce the motion, while for kinematic analysis, we don't. A typical example that heavily relies on kinematic analysis would be animation. For instance, say now I want to simulate the motion of an animal walking. What is the corresponding mechanism that can help me to achieve that? Or to be more specific, how many rigid bodies are needed? What are the geometry properties of each rigid body? How should these rigid bodies be joined together? These are the questions that often occur to an animation designer. But is it necessary to care about the forces that produce the motion in animation? The answer is clearly no. However, in real-world application, we do need to care about the forces that produce the motion. For example, say now I have designed a slider crank mechanism whose motion follows a given trajectory. What will be the corresponding force or torque if I want the slider to oscillate with a specific magnitude and frequency? And at the meantime, how large will the joint reactant force be? These properties would be crucial to the materials and motors we choose to build the mechanism. Okay, we're done with the difference between kinematics and kinetics. Now let's get our hands on dynamic analysis. If you have learned dynamics before, you'll realize that when it comes to dynamic analysis, it is no harder than these two equations and these two steps. But in hope of no ambiguity, let's do it together one by one. First, let's draw the free body diagram of rigid body 1. The forces acting on rigid body 1 are joint reactant forces Fbx, Fby at pin B, and Fox, Foy at pin O, gravitational force m1g, and the applied torque T1. And according to the free body diagram, we can come up with these three equations. Next, rigid body 2. Again, let's draw the free body diagram. The forces acting on rigid body 2 are the joint reactant forces Fbx, Fby at pin B, and Fcx, Fcy at pin C, and gravitational force m2g. With the free body diagram, we can again come up with these three equations. Last, rigid body 3. The forces acting on rigid body 3 are the joint reactant forces Fcx, Fcy at pin C, gravitational force m3g, normal force n, and torque tau. Now we can derive these three equations. Note that the reason why there is tau is because the slider cannot rotate with respect to the ground. Therefore, a constraint torque tau is needed to cancel out the torques acting on the slider if there's any. Also note that I didn't talk about the ground, and the reason for that is because ground is often not our interest when it comes to dynamic analysis. Now with these 9 equations, we should be able to analyze the dynamics of the linkage system. But if we take a closer look, we will realize that there are 17 unknowns in total. We cannot solve 17 unknowns with 9 equations. Clearly, if we want to solve for these 17 unknowns, we need to have 8 more equations. In fact, the missing 8 constraints are from kinematics. And this totally makes sense because we know from kinematic analysis that the motion of the linkage system is constrained. Therefore, besides Newton's equation of motion, the acceleration of the system should also satisfy these 8 constraint equations. Note that since in dynamic analysis, ground is no longer relevant, the original constraint equations we derived in kinematic analysis should also be revised to omit ground's component. Here, revised equations have been marked with red underlines. Okay, so that's all for the introduction to dynamic analysis. In the next lecture, we will show you a technique to help you to solve all these 17 equations.